So for this problem, we were asked to... So I did these steps, and I'm assuming that the comments were in regards to this one, where it asks, what value of R do you suppose would result in the maximum power being delivered? So what I did was, this was our power function that we were given. We established right here that the value for R will be equal to whatever R takes. So in the thing that we were given, we can see that we had the value of 14 ohms for this R, which means that this R should also be 14 ohms. Now, hopping back over to here, we can see that we took the first derivative to verify an extrema point, and then with the, where is it? We verified that there was an extrema point by setting the first derivative equal to 0. We took the second derivative to determine the concavity of the curve and found that it was a concave down, meaning that we were at a peak and it was going to decrease in either the positive or negative x direction you traveled. So I wanted to verify everything that I was doing here graphically. So right here we have a function that you can see, which is, let me adjust my window size here. We have z is equal to 9 times x over x plus y squared, and those values map directly to this power function that we have here. The value for E that we put in was the 3 volts from the experiment squared. We get 9. I use capital R to be mapped to x and lowercase r to be mapped to y. Now we are already given a y value that is held at 14 ohms. So if we go over here and we look at this plane here, we know that our point has to exist somewhere along where our function for power, being this one here, and the y intersect. So somewhere along this line here, again, this line we need to find an x value, and those x values would be our r value for where we find the maximum at. Now, we said that r should be equal to r, which means that the point should exist right there, and then if you plug in those values for x and y into our function, we'll get a z value of this, which if you were to zoom in, you can see that it goes right to that maximum point. And then as a point sets, I just put the point there. So it's really, really hard to actually see that we are indeed at a peak here, given the constraints that we have. So what I did was I took this, and we're just going to scale everything up. We're going to multiply it by 1,000. And what we can see here is if I toggle off this one and that one, but we'll leave that on. We'll leave this one on. You can see that there is this sort of curve that goes up, 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 and then it starts to, at some points, presumably right here, that being the peak, it decreases. And again, if we zoom out, you can kind of see this curve here that goes like this. And so the R value given our Y value for where we will hit the peak Z value is right there. And actually, if we were to scale this, I think by 1,000, hopefully that, oh wait, you know what? Wrong spots. I need to do that in here. So if we scale this by 1,000 here, that should fix that. No. It's not by a factor of that. It's going to be, I could just throw this into a calculator. So let's see. 1,000 times, I've got 14 divided by 28 squared. We're going to get 17.8571. Yeah, okay, 17.8571. So if we edit this point here to be, yeah, so we would get, so given a y value of 14, where is the peak occurring? Obviously, if we look at it from this perspective, if we rotate things, we could say that there's a better maxima over here as we decrease y, but we are restricted by our given y here. So again, if we really wanted to maximize it, we would start to minimize y. And then as we minimized y, anyways, that's I'm getting a little bit off track here. What I really wanted to show was that given that our y value, again, y matching our value of 14 ohms, what x value mapping to this large R would we get? Again, we showed this in here. We found the extrema by doing that.